So hi, I'm Ken Little. I'm Director of Product Engineering at Tumblr, which is a reasonably popular blogging platform that grew up quick over the last couple of years. So I'm going to tell you a little bit about what we went through during that scaling process, both from an engineering perspective and also organizationally. So very quickly, what is Tumblr? So like I said, it's a blogging platform with a social component, so you can follow blogs that you like and see a real-time feed of that. Tumblr aims to make blogging simple and focus on creativity by encouraging people to focus on the 7 post types that we have. So obviously, text, photo, quote, video, that kind of thing. For the blog side of Tumblr, we allow a lot of customization. So you can come and you can create a blog. You have complete and total control over the theme of that blog, everything from the HTML to the JavaScript and the CSS, which is a lot of fun to manage. From the consumption side of Tumblr, you also have this dashboard, which you don't have visual control over, where folks come and follow blogs that they're interested in and see more sanitized versions of the posts that are coming out. So the stats today, Tumblr's in the top 15 for reach. We do about 18 billion page views a month. Our peak request rate is about 50,000 requests a second and 2,000 posts a second. We do about 70 to 85 million posts a day. And we have about 100 million blogs on the network as of a few weeks ago. And all told for engineering, we have about 80 engineers supporting that stack. And the path to that came fast and furious around the turn of around 2011. So Tumblr's been around for about 7 years. And the first 5 years or so of that, it was a typical startup. And as it gained steam, it hit about 2 billion page views a month in 2010. But then after that, you can see things really accelerated, started to pick up both in uniques and traffic. And that necessitated a lot of growth in the way that Tumblr approached its project. So Tumblr started off as a pretty typical startup, very simple architecture. And almost all of the growth and evolutions in technology that we had to go through were all born from necessity. So they all came out of problems that were immediate and that were pressing and that were keeping the platform from growing more. So it's a very organic approach to evolving a tech stack. So as it started to take off, the main challenges that the application itself faced was high data volume and a legacy PHP code base, which, as most pieces of startup technology, wasn't exactly the cleanest. And a more fast-paced growth coming. So you had to really try to get ahead of the curve in order to meet the demand for the product. Procedurally, especially in the last year or two, we had a fast-growing team, total and complete demand for fast change cycles. So there was no time to sort of sit back and re-architect or recode anything. The new features and the new improvements to the site had to get out very, very quickly. And a fast-growing hardware footprint. So obviously, with that much traffic growth, you're going to be throwing a lot of hardware at the problem, and that in and of itself becomes a management problem. So scaling the app. The way that I think about this is over the last 3 years, Tumblr really had to go through plateaus of scalability. So in 2010, when you're sitting at 2 billion page views, and the growth really starts to take off, you know you're growing, but you have no idea where the ceiling is, right? So whenever you're sitting at 2 billion page views, you look at your app, you see which pieces of it are falling apart, and you try to figure out what you have to do in order to hit 5 billion, right? And that's your first plateau of scalability. Then, a few months later, you hit 5 billion, so you try to reach the next plateau of 10 and next plateau of 20. And as you're doing that, obviously you're going through and changing key components of the architecture, but never more than what you have to do. And you're always trying to keep the app as simple as possible because you're not too sure where you're going to have to pivot down the road in order to make the next plateau of scalability. So just focusing in on 2010, the app looks like what you would think a very simple web app would look like. It's a relational DB, mostly centralized in one database. There is some functional partitioning, so you might have the users tables completely separated from the tags table, that kind of thing. But you're still doing a bunch of joins. You're still doing aggregate queries off of your core data. whenever you want to see counts or anything of that nature. And there's very basic real-time monitoring analysis that people are tailing logs on servers with little aggregation because the hardware footprint allows that to succeed. It's small enough. And you have a lot of manual configuration for hardware. So 2010 architecture looks pretty straightforward. Master-slave architecture, some MySQL, not a lot of caching, and a pretty simple web stack up front. Everything happens in the app. It's all monolithic. It's all synchronous. So if there's any write, it's all as data is actually coming in. There's no back-end processing going on. So the first issues that Tumblr started to hit, too many posts for one database. So the posts are obviously one of the biggest pieces of data that we have to store. And that's where storage constraints started hitting their limits the quickest. And the second was aggregate filters and lookups. So on Tumblr, on the posts themselves, there are two pieces of aggregate data that are on every post. And you can have somewhere between 10 and 15 posts per page. And you have to do these lookups for, in the upper right-hand corner, you get what are note counts. So things that people can do on a blog. They can reblog it, they can like it, they can reply to it. And all of those roll up into the note count for what kind of actions happen on the post. Well, that starts to break down once you start hitting a reasonable amount of volume. And then at the bottom, you can actually see a breakdown of all the notes. So now you got to go for each post and pull those in something that approximates real time in order to have freshness. And those two things start to really fall apart. Oh, that guy's out of place. So what do you have to do? Well, whenever you see this kind of growth coming your way, you're sitting there and you're seeing that curve starting to really take off. Obviously, since the posts are your biggest problem, the first thing you start to do is shard the post data because you have a data storage issue, right? So all you do is you take your posts, you shard them by the blog ID, and now you can push those out to various databases and actually extend your storage capacity that way. But obviously, this means that you lose your ability to do joins. So you have to move to mostly primary key lookups and start doing all your joins in the app. Same for filtering, right? And you also have to move to having an index table separate from the key post data, right? So that you can actually figure out where different posts are and still do chronological lookups. And you no longer get to do auto increment on IDs, so you gotta kick up a ticket server or an ID generator, that kind of thing, so that you can assure UUIDs for your posts. So the 2010 architecture, by the time that 2011 came along, looked something that was a bit more like this. So you have your post shards down below. You have your Memcache servers doing a lot more work, and Redis was introduced not too far into the later part of 2011. And an index database so that you can do lookups without having to query all shards. And for the aggregates, which were causing you trouble, you introduce a couple of services and start moving toward a service-oriented architecture, specifically for the note counts and notifications. And all of that actually ties back in and into the core data stores and provides additional caching and roll-ups. So next up. So again, you're still sitting there on a fairly monolithic application with all of your writes, be they the core write of just getting the post into the database, or the ancillary writes of incrementing your note count counters, or pushing off that data into secondary data stores, and you still have this monolithic index, which as Tumblr continued to grow, even the index table for the posts became a storage problem. And obviously more services. So you're trying to take all of these writes that you have and push them off into services so you can actually break them out and control them, and they don't become points of failure that bring down the whole application whenever they have trouble. So 2011 and parts of 2012 saw us introduce a number of considerations for that. So obviously some sort of asynchronous worker pool. For us, we chose Gearman. More services, so that I won't go into the detail of those, but you get the idea. For anything that's sort of an aggregate or a secondary data structure, we tried to produce services for them so that we didn't have to do them inside the app. And sharding the index table. So sharding the index table was an important step And what it solved for us was still a data storage problem, though, right? So it doesn't help you with concurrency. It only helps you with your storage footprint to push those things out, and I'll tell you why in a second. So at that point, we're done, or not. So like I said, Tumblr has two key components. You have the blog view, where you see only one blog at a time, and you have the dashboard where people are actually following in real time, and an asymmetric graph of folks that can be arbitrarily large. And the second half of that, the dash, is what's seeing the most growth. So 70% of all traffic is going there. And the blog view is pretty straightforward and pretty simple. You've already sharded out your post by shard. So all you got to do is go to one database and pick up the post for that database. There's no authentication. There's no personalization. Everything here is very, very flat. It's linearly scalable, and it's cacheable by something like Varnish or any other kind of edge caching solution that you can think of. So this part of Tumblr architecturally is pretty much solved and dealt with. Now the dash is a completely different story. So it's an arbitrarily sized asymmetric graph. People can follow pretty much as many people as they want. You have to do a global chronological sort on the posts. People are always sort of looking at that top head of what's happening right now. And because it's time sensitive, you don't get to cache it. So it's sort of the worst of all worlds. You have a centralized, you have to go to a centralized data store with the current architecture in order to know what you want to show people, and you don't get the opportunity to cache it. So every time they come back, you got to show it to them. You got to run those queries again and show it to them again. So you're looking at a ceiling, right? And this is a ceiling that Tumblr has been dealing with for many years at this point. And we are still on the core architecture that's shown here, where we have the sharded index tables, which are the main point of concern, because they essentially have to be sharded by time. And because of that, everybody who's going to go to page 1 of their dash has to hit whatever is the head of that index shard right now. And that's a problem. So we've been able to optimize our way into extending that architecture for quite a while, but it has an end of life. There is a point where you can't add another read slave to the head of that index shard, and there just is a point where this solution starts to break down. And we've come up to that point and pulled back a number of times with just by starting to pull as much query and processing out of the index tables and push them off to other data stores whenever possible. So the dashboard view, why is it so challenging? So right now, the dash is essentially all of the complexity goes into the read view of the dash. So whenever people post, we write the post once to whatever shard that is. We put one entry into a global index table. And then whenever you come to actually view your dashboard and see your timeline, we go pull all the people that you're following. We pull all their recent posts. And then we essentially do a merge sort and show you that in real time, right? So obviously, you have a simple write, and you have a complex read. And if you're ever going to get to the point where you can do more reading, which is what you want to do, you have to push that complexity the other direction. So essentially what you have to do is get to the point where your complexity is in the right and your read is dead simple. And you would do that with something like a materialized timeline from the post. So instead of writing into the index table once whenever someone posts, you would actually have a timeline for everyone that followed them, and you would have to write per follower every time someone posts, right? Which severely complicates the write path. People can have, many followers. At the high end, you're talking hundreds of thousands or millions of followers. So taking one person writing and turning that into one person writing a post and turning that into a couple 100,000 inserts into various index tables is a rather complicated endeavor. And even this doesn't really get you out of the problem because of those people that have a high number of followers. So you actually have to have some sort of mixed approach where for people who have a reasonable number of followers or don't update all that much, you can take and materialize all their rights for the people who are following them immediately and actually do that work for the timeline. But for the folks who are truly, truly popular on the platform, you're not going to do that. You're actually going to hold them off to the side, and you're going to inject them into their followers' timeline at read. And this is not a new approach, and it's not a problem that's unique to Tumblr. A lot of products out there that have asymmetric graphs like this and want to show real-time updates have this problem. There's a really great paper from Yahoo from a few years ago called Feeding Frenzy, which details their learnings on essentially partially materialized timelines. They were doing it for my Yahoo, where people were following RSS feeds. And but it's a pretty similar, the analogy is pretty straightforward for what we were doing as well. So where are we going? What kind of architecture could possibly make that happen? Well, if you want to move to essentially a mostly materialized view inside the dashboard, then obviously you have to divorce your reads from your writes completely. So whenever somebody actually comes to post on Tumblr, you have to give up the idea of a globally consistent view of the data set and move to an eventually consistent one. So at least for one user, what they see in their timeline is always consistent, and it doesn't flap whenever you're refreshing the page or coming back. But across various users, posts might be showing up in a slightly delayed fashion. So you're going to take something that looks like this and move, hopefully, to something that looks like this, where obviously everything has to sort of become much more stringently service-oriented. And you're going to take any write that comes in the system and push it into something that we call the fire hose, which is something that just takes pretty much any write, be it a post, a like, a follow, someone registering, any event that's manipulating data, and it's shoved into the fire hose, and then it's passed into a series of data processors, right? So you would have a multitude of listeners hanging off of that fire hose, looking out and filtering for the various events that they care about and acting on them. So obviously something would go in and spawn off maybe a number of workers to put in indexes into people's timelines, and another would increment post counts or note counts. Others might do some logging or some other aggregate data manipulation that you have, and write those out to stores down below. And the other half of what you have, well, don't have to do, but ideally would do, is move to something more like HBase for those materialized view indices. And then all reads would have to take a different path and would essentially be completely, you'd move to the eventually consistent model where for each user they're seeing something that's stable for them but not necessarily globally consistent. So the fire hose is actually a pretty cool technology that we built up and have been evolving since 2011. You get the added benefit that this is pretty valuable information that a lot of people want, and so we, like Twitter, have the fire hose available through a third party. So you can actually grab it and listen to all the data going through Tumblr and filter it yourself and see what's going on. Okay, so if we were going to actually do this, what kind of capacity planning would we be talking about? Well, we're just on the low end. Let's say we're doing 70 million posts a day, which is higher now. And on average, you get 500 followers per blog that's active, which is a little bit of an overestimation, but you kind of want to do that whenever you're playing with capacity plans. Something like 1 kilobyte per post with a 0.04 with a 0.4 compression factor. And obviously, if you're dealing with HBase or something based off HDFS, you're talking about a replication factor. So we did 3.5 for 3 replications plus a little bit of scratch. And the only number that's if like the bottom chart here is the one that's sort of most interesting to me. You're talking about picking up, and this is just in indices alone. This isn't actually dealing with the posts. It's essentially just mappings of longs, right? You're picking up 1.5 terabytes a day of index data, or about half a petabyte a year of data that you have to store in perpetuity. So it's a non-trivial problem. All right, so that's sort of the core app. So we're still hanging out on the sharded indices. We have a number of the key components in for the projected architecture, like the fire hose, which is key. We have a number of other places where we've used HBase, so we've picked up a number of key lessons there about what it takes to use that technology in production. So things are looking good. But then there's the other half of what we've been doing in the last couple of years at Tumblr, which essentially is large-scale batch processing. So we have a tremendous amount of data that we want to act on. We either want to have business intelligence on it, or we want to provide analytics for our users on it, or we're going to turn it into a product and see if we can actually take the data that we have and turn it into recommendations, or help people find more content that they're going to love on the network. So we have a Hive cluster that sits at about 750 terabytes. We keep about 12 months of historic data in there. And whenever we aren't pruning it, it grows at about 2 terabytes a day. So we'll let it grow up and then prune off a couple of months and keep going with it. It's mostly populated with table dumps and with just a ton of logs from Scribe. We are heavy users of Scribe for informational logging. So we're using that data store to produce a lot of internal BI, to do spam detection and any sorts of correlation between users or blogs or posts, advertiser analytics, any sort of targeted email campaigns. So if we want to actually pick up and do some marketing email, we'll go into, and instead of using the live data for that, for determining who we're going to target, we'll actually go into this data store and do it. And through a number of ways, we're powering a few searches that we're kicking up online. So we Tumblr started off with very simple searches, like you can imagine, light queries, that kind of thing. That fell apart pretty quick. So we essentially had to take a lot of search off Tumblr, and we're just now in the process of getting that back in line. So, and this is just even in the last couple of weeks. So up until the last couple of weeks, we essentially had a tag search. And that was about it on Tumblr. You could look up posts by tag, and that was stored in a global index, and it was limited. You could only really tag, you could put 5 tags in any post, and then we only indexed original posts, which is a much smaller subset of the corpus, since there's a lot of reblogging that goes on in the network. So in the last couple of weeks, though, based on an architecture I'll say in a second, we got a number of new searches out. So key components here. So this is a blog results page for just looking for the phrase tech. So this search is a small percentage of the data that we have, mostly blog name and blog description, that kind of thing, for that phrase, and returns it. But it factors in a number of things, even in its view 1 state. So it factors in your network graph, and it factors in the frequency of posting for the blogs, and the relative popularity of that blog to try to give you more relevant results. And that's something that we, now that we have the framework for it, we can actually evolve that and do more interesting things with targeting. And the other thing is type ahead. So we have the same type of ranking going on with all the tags that we have regarding popularity and how many people are posting original content to those tags or searching for them. And so whenever you start to type in the search box, we'll give you type ahead for and suggested tags for that phrase. And so all of this, while we did try a couple of more conventional search technologies, we ended up doing something custom for it. And it's the same architecture that we've essentially gone to for all of our large-scale batch processing, and it's worked out pretty well. So all the apps, anything that essentially can manipulate data, be it the services or Gearman or the web app, anything, throws a ton of logs into Scribe, which we then consolidate along with the core tables into Hive, and in a couple of cases HBase. And then on a periodic basis, depending on the problem that we're solving, we just have a number of worker boxes that are essentially running crons that will pull that data out and aggregate it. So if it's a search index, it's going to be looking at all the new blogs cropping up or all the blogs that are actually active and tying them together with the search terms. and then throwing that into primary data stores and aggregate. So we've really started leveraging Redis a lot. It's a pretty fun technology, and for this kind of thing, it's great as long as you have boxes with sufficient RAM, and you can deal with the fact that you essentially have to shard Redis on your own as well. So, which are attributes of it that we've done. And from there, the apps actually pull back in and use them, use that aggregate data to do real-time features. So, anything from analytics for advertisers to search features will go sort of through this path to make it back out as a feature. And that's the app for Tumblr. So, what did it take? On the other side of things, what did it take from the management perspective to take this path in Tumblr in the last 3 years? Well, Tumblr was a small company for a very long time. As recently as 2010, there were 5 engineers on staff. By the end of 2011, that was 25, and by the end of last year, that was up to 80. So the majority of the staffing and the majority of our ability to sort of fan out and tackle multiple problems at once, especially legacy problems, came in 2012 and now in the first quarter of 2013. And with that, you had a lot of complexity in the hardware stack and the number of people just touching things constantly, right? So one of the biggest growth pains that we had was automated MySQL topology. Right? So at this point, we have somewhere in the order of 250 databases, and that's grown up over the last couple of years. And that requires a lot of management. So every MySQL database that you have has a couple of read slaves and at least one backup slave that you can pull offline and then do a dump of and show that up to cold storage. Across the board, it's about 80 billion rows of data and about 30 terabytes of data. So it's a fair amount of management that has to go into it. And the way that we solve that problem is with something that we call Jetpants, which is essentially a command line set of tools that leverages something another tool that we had to build called Collins, which I'll talk about in a minute, to manage master promotions or new slaves or shard splits. So it essentially is a tool where you can sort of point it at a database and say, okay, you need excuse me, you need a couple of more slaves, and those slaves are going to have to get booted up. They're going to have to get caught up from bin logs, and they're going to have to get put into the proxy rotation and the app configurations so the app actually knows to hit you. And Jetpants manages all that for you. So it's a pretty important piece of technology that we've had to leverage. Doing all of this by hand obviously became untenable sometime in mid-2011 or so. Once you have more than just a few MySQL databases, you don't want to be messing with them by hand if you lose a disk or if you're having issues with read traffic, for instance. The other thing that we had to deal with was the dev cycle. So in 2011, you have a pretty small team. They're working on long-lived branches. They're just building out features or whatever core piece of code they're trying to deal with. You have one deploy a day, executed and monitored by ops. So engineers are fairly abstracted away from that process. They commit into master. Essentially, a release engineer on the ops team will go grab that code once a day and deploy it to the site. And the release engineer is responsible for watching logs and watching graphs and trying to suss out whether or not anything that changed in that push broke anything, and then tell the right engineer, which requires a lot of knowledge about what's going on. And that's where things start to break down as you get a bigger team. If you have a release engineer, he can keep up with what 5 or 6 people are doing. But once you get up into the 20 range, it's impossible for one guy to know what 20 people did over a 10-hour period the previous day that might, or even longer, that might have an effect on the site that can't be predicted. And then hotfixes were done throughout the day, only if needed. So you really had this sort of daily cycle. So what we have now, short-lived branches that are measured in days, hopefully not even that long. Ideally, everyone at Tumblr is committing into master at least every second or third day at the longest. And part of that is because of the idea is to keep small change cycles, small change sets, easily reviewable change sets, easily rollbackable chain sets, just to make sure that you actually know the impact of your change and can deal with it if it causes a problem, and you don't build up large chain sets that are hard to sift through if there is an issue. Configs are generated from columns, and every machine in Tumblr has in columns the SHA of the latest version that it has, so you can go through and validate that every machine got the right push. Pushes are done throughout the day, and they're managed and monitored by the engineers who wrote the code that is going out. So we're pretty dependent on IRC at this point, so people will jump into a push channel in IRC, and we have an IRC bot there that helps them actually jump into a couple of groups and manage the push cycles that way. So you get 2 or 3 people that are actually going and pushing, ideally less than 1,000 line changes at any given time. Because you are asking people to merge into master constantly, we have a flagging feature that we call the Dude Ranch that lets people flag off their changes so that ideally it's either completely unreachable, it's totally dark, so that the only bar you have to hit is that you don't have compile time errors because you're actually nothing is executing it, or you can turn it on in production for yourself or your team or for all admin, and eventually percentages of users by either user ID or IP or however it is you need to slice up the feature that you're trying to launch. And that's sort of one of the great benefits of this approach to dev. Once you sort of ask people to commit into master, and you have to have this mechanism for dealing with code that's not really ready for the world to see yet, then you force people into building features that are constantly backward compatible. There's no option. You have to be backward compatible with your changes, and which means rollbacks are not a problem. You get the ability with this flagging structure to roll it by percentage. So you're never really caught off guard by a scalability issue or by a feature that doesn't do quite what you did, because you're going to open it up to 5% of users and you're going to watch it for a couple of hours, and then depending on the complexity of it, ramp that up either through days or through hours. So recently we redid all of our post forms to be more Ajaxy. They were a little dated, and that lived as a feature for Tumblr admin for 6 or 8 weeks before it ever saw the light of day, and when it did, we ramped it up over 3 days. So people were actually seeing it, and we were able to respond in real time to edge cases that we hadn't hit, even with essentially 100 some odd beta testers inside the building, beating on the feature for weeks on end. So we have a web app for deploys. And so you can see from this example, so Johnny's pushing the site. He's going to hit about 1,000 machines doing it, and he's through almost 800 of them. And we have all of the hardware, the site, essentially sectioned into a number of key groups, right? So even with the configuration flags that we have, we don't roll out to the whole site at once. We start off with a small section from each pool, so an edit pool or a read pool, and that'll be Web A, and your change has to go to Web A first, and that hits about 20 machines. And then you're sitting in our monitoring tool, which is based off of OpenTSDB, or you're sitting in Splunk, ideally both, pretty much anything along the top there, and you're watching your graphs for Web A, and you're watching your error logs for Web A. And if there's an issue, there's not an issue, you just pull it back, right? So ideally, if you've got a change, you find out on Web A at the latest, and roll it back, and that's it. 20 machines were affected. A small percentage of traffic was affected, and you caught your problem early. So with ramp deploys for the configuration system, so this is a pretty simple example of us adding a configuration that we're going to ramp up. So for us, this is the new search that we pushed out. And as you can see, it's pretty simple. All it does is it takes the name and it takes a callback function, which you can define in line. And this one's pushing out search to 25% of user with a simple mod. And to use it, you just do a dude win on that guy passing in the right parameters. So it's completely customizable to the feature that you're trying to ramp up, since it's callback based. And it's pretty straightforward on how to deal with it. And if you were, and this one was for friend search when we pushed it out, but if you were in that, you'd actually get to go to the friends page, and if you were not, you would have gotten a 404 for this until it was time. Trending and graphing. So this is an internal project that we call Fiber. This is essentially a graphical front end on top of OpenTSDB, which is what we use to store all of our essentially health metrics. And in this particular instance, the vertical lines that you see here, these are deploys throughout the day. This is a 24-hour period, and every blue line is somebody deploying Tumblr or the configuration repo to the site. So when in a smaller time frame, which you can imagine is that you would go to this, and in a 1 hour or 2 hour window, you'd be watching your 200s or your 500s or any metric that's sort of key to what you're doing, and you'd be able to see immediately where your deploy started and whether or not that correlated to a change in the graphs that you need to go investigate. So it helps us tie together pushes to problems on the site and keep an eye on what's going on. We obviously have a ton of Nagios monitors. The most interesting ones to me are the Nagios monitors that are based off of thresholds in OpenTSDB, so you can actually fire off alerts, say if your registrations drop below a threshold, or you detect in OpenTSDB that you're having issues with login. Those sort of second order metrics, more so than just sort of I/O checks or CPU checks, have become pretty crucial for us. And then there's Collins. And so Collins is essentially automated provisioning. So all of the hardware is tied into Collins. It's essentially a one-stop shop for the hardware that we have. It has all the information you would ever want to know about a machine, including its specs, how much CPU, how much RAM, what kind of disk, where it is, which rack it's in, what's the rack position, pretty much anything you want to know. And as an engineer, you can go in and shop around in the open, unallocated hardware. And if you've got a new project kicking up and you think that you need 3 more Redis instances, you just go into Collins, choose machines with the right profile, allocate them under the appropriate role, and all of the systems tie in to Collins so that whenever that's actually done provisioning, it'll get put into the right load balancer stacks. It'll get put into the right graphing groups. If it's a machine that needs to get deployed to, it'll get put into the right group. So, for instance, if you had to tear down a machine that was in the Web A group and build one back up, that would happen automatically. And everything, even our logging systems, have those grouping structures that are automatically tied to from Collins. And then there's metadata that's annotated here. Services annotate here, like deploy. So whenever a push is made, deploy will come and actually write in that SHA so that you can query Collins and find out if any machine's out of date. And before Collins, I'd say one of the most interesting problems that we had was just the drift that happened as the hardware footprint grew, and before we had automated management for that hardware footprint. We had engineers and ops engineers manually maintaining configuration files for deploy groups that a machine was in, and also proxy pools that a machine was in. And whenever you're doing that manually without a centralized data store like Collins, you obviously get drift. So we would have, if we had, say there's like two core pools in the main app, and that's the read pool, which we call the dashboard pool, and the edit pools that any actual write will go to. If you had, since you have like the distributed configuration there, you could very easily drift from what one service like deploy thought a machine was compared to what one of the proxies thought it was. And Collins solves all of that. So it's all coming from a central server. Everybody knows what it is. All the services tie into it. And there's absolutely no drift, which matters once you have a footprint of a couple thousand machines. So everything that ties there. And those two applications, Jetpants and Collins, are actually open source. So we have them on our GitHub page along with a number of others. They're really useful tools. I think that they're problems that a lot of companies face, and while they might not solve your exact problem, you can at least go check it out and sort of see what we did and how we solved it. So open challenges, things that are still left. So we're still working on better searches. That's obviously a key component to us. Discovery is really, really important on any sort of content network. Related content and recommendations, more real-time reporting, and behavioral analysis and A/B testing to see how people are responding to the features that we do. All of which at our scale, especially whenever you're trying to do real-time analysis on how people are consuming the site rather than producing for it, require the next level of architecture for us. Tools that we love. I think the one we've talked about a lot of them. So our backend services are in Scala with Finagle and a number of other great libraries that are out there for Scala. The front-end app is essentially a LAMP app still, anything that's not sort of pulled out into a service. And Kafka is a really great, an important piece of technology that powers the backbone of the fire hose. So that one enabled us to do a lot. And core lessons learned as we went through all of this. So nothing performs as advertised at scale. Once you start throwing tens of thousands of requests at a given piece of technology, you're going to have to pay attention to what it's doing and how it's doing it, and possibly end up tweaking it and tweaking how you're using it, which is not a bad thing. It's just you have to give yourself that leeway when it comes to learning how to use these technologies in your stack. Automation is hugely important, especially when it comes to hardware management and knowledge about what the hardware is doing in your stack and where each piece of hardware sits, even physically, once you have a few thousand machines. Open channels and metrics. So I think culturally, one of the biggest changes that we made was shifting the responsibility of monitoring pushes from a release engineer to each of the developers that were actively pushing code onto the site at any given time. So the entire engineering organization had to learn about, first of all, where the graphs lived and how to read them, and also what graphs existed, and how their site, how their change might affect various pieces of the site they haven't thought about. Since they're pulling up and looking at a number of dashboards at any given time, sometimes you can see changes affect pieces of the site that you really weren't expecting it to just by watching the graphs constantly, and not even the graphs that you thought that they would affect. Operational tooling, really important, and yeah, automation and good operational tooling can allow a small team to build really amazing things. So we're still sitting at 80 engineers, which for us is essentially over 1 million blogs per engineer that we're supporting, and we're able to do that in part because of all the automation and tooling that we've sort of put in place to manage it. And that's it. Any questions? Yes.
So you might have an obvious answer for this, but what happens when you want to upgrade, say, a library you're dependent on? Say you're upgrading jQuery from one version to another, and that's obviously going to affect a lot of the site at once. How do you manage that?
Yeah, so the question is, how do you manage library upgrades? And specifically, jQuery, for instance. Well, I mean, it really depends on where in the stack the library falls, obviously. So if it's in the PHP stack, then you're golden. You can actually you're going to have to go to where that library is used and wrap it in a dude and ramp it up that way, and try to have both versions live at the same time. Recently, we moved from prototype to jQuery on the front end, and it's a lot trickier whenever you're pushing around JavaScript, right? You don't necessarily have the options to flag things off the way that you do in the PHP layer. And even that, we managed to find ways to flag it off and to ramp it up by user. So you essentially, I mean, for us, it came down to just finding ways to get those configuration variables out into the JavaScript layer on a conditional basis, and then trying to do the right thing from there, right? And coordinating between what was included on the front end and what was included on the back end. But I mean, the name of the game for us is to try to push all changes out incrementally, even if it causes a fair amount of complexity in how we do it. And I would say moving from prototype to jQuery took us maybe 4 months to do it feature by feature. And while we were doing that, it was obviously you're downloading both libraries. So there's on the front end, and prototype's not small. Well, jQuery is a lot more manageable with, but prototype's, you know, a couple hundred K of additional bloat that you're downloading when you know you're trying to retire it. Yeah?
What kind of load balancing solutions do you use?
What kind of load balancer solutions do we use? So up at that layer, pretty much everything is HA proxy. And from a hardware perspective, I couldn't tell you like what kind of equipment they're using for it. Yes?
Has mobile created any unexpected challenges with this architecture, or is it just another type of client plugging into what you're doing?
Yeah. So has mobile created any complications with this architecture? So for us, our mobile clients tie into our public API. So in that respect, the mobile APIs have very few hidden endpoints that are only used by the client. One of them would be like registration, for instance. But we essentially eat our own dog food with the API. And that our API is essentially just another view on top of the standard web app. So there are a couple of customizations that go into the controller. And obviously the views are completely different. But other than that, it's very, very similar to how we manage the front end. I would say our mobile apps went through an evolution, right? So and during the same time frame. So the first one that we had a couple of years ago, both for Android and for iOS, essentially had very little native components in it. They were essentially just drop-in WebKits and web views. And because of that, you had a lot of the same harnessing available to you because you were just loading a web page on your site and on the phone. And as we moved to native about summer of last year, it added additional complexity in the sense that you don't really get to ramp up features for the device. I mean, developing for mobile, the cycles for developing for mobile are completely different. So you're moving on, especially for iOS, given the overhead of waiting for waiting for Apple to give you their blessing, it makes it a much different release cycle. So we do our best to build into the app the ability to behave differently depending on what's coming back from the API, but we don't try to push out configuration management or flag management into the apps themselves. It's just, if a piece of information is available in the API, then use it, and if not, don't use it, and we'll control with flags what information is going back to the API. Yeah?
What do you use for virtualization?
For virtualization? Well, we don't actually have much, but for what we do have, I have no idea. Yeah?
Okay, so in Collins, you were talking about provisioning hardware. Is there some sort of manual approval process there, or does it just go ahead and allocate whatever you ask for? Because I imagine if you don't have the resources available, or if someone decides that they want to provision 100 servers and someone else says, well, only 50 are needed.
Yeah. So the question is, do we have an approval process in Collins? And the answer is no. There's a social contract, which is don't be a jerk. And you can't allocate more servers than what are there. Obviously, so for instance, if you think that you need a new Redis class machine, you're going to go look for unallocated Redis class machines, which is queryable, and then you're going to see how many you have available to you. And notifications are kicked off. There are a number of people who are in charge of making sure that we have enough machines available at any given time. And typically, you're going to have a conversation with them before you do any allocation in Collins. But it's a social agreement, and that's worked out pretty well. I mean, people know, that there are considerations in hardware and need to have a conversation. But it's it's better to have that, at least for us, it's better to have that framework available and not have a technical barrier to doing it, so that once the conversation is had, anybody can sort of manage their own process. So if I know that I need 3 and I talk to the ops guys and they say I need 3 Redis servers and they say, sure, go right ahead, I can then go into columns whenever I'm ready and kick them up, and it's going to be good. Yeah?
So you mentioned that you separated the index data from the actual posts. Was the index data still part of a relational database?
I'm sorry, can you say it again?
Was the index data still part of a relational database at some point?
Oh yeah. Well, at least right now, yeah, it's all sharded in MySQL. So essentially, the index databases themselves are sharded in MySQL databases with a ton of slaves. Yes.
You mentioned the rolling rollouts that you were doing based on user. When you do you do anything like that on the services layer already?
So we do. So the question is, do we do rolling rollouts at the services tier? And the same strategy that we apply here, we apply to the services tier. We'll typically do the controlled rollout in the app, though. So we'll have both versions of a service running at a time on different ports or possibly different machines, depending on how severe the changes. And then we'll toggle between the two with a rollup. And even though the Scala services don't use the same deploy infrastructure as the PHP app for obvious reasons, I mean it's a completely different kind of push process. They still have ways to do it, and typically in Puppet they'll deal with those rollouts and try to target a number of machines, try to make sure anything that they have is still backward compatible, which is a really key piece of the whole thing. Like a breaking change is a really, really rare event for us. Everything has to essentially be backward compatible. Anything else? Okay, thank you guys.